So I welcome Irina Bobkova, who will be talking about invertible E2HC4 modules.
All right. Thank you, Dan, and thank you for organizing this seminar. It's very nice to see people, even in this format. All right, so I will talk about the car group of E2HC4 modules. And I'm sure it's familiar to many of you, but I will very quickly introduce what E2 and C4 are. So we're doing chromatic homotopy theory, and GN is the Morava stabilizer group, and EN is the Morava E theory. Okay, and then if you don't know what these are, that's okay. It won't really matter for most of the tools I will be talking about. But I want to talk about is for motivation. And for finite groups, so Morava stabilizer group is profinite. It has some finite subgroups. And then the fixed points with respect to those finite subgroups might approximate the fixed points with respect to the entire Morava stabilizer group, which is the Kn local sphere. And they might also be easier to compute. Okay, so this is a very brief two-line motivation for why this spectra of this form are interesting. All right, so these spectra are ring spectra. And so we can consider the category of modules over them, and then we can ask, what is the Picard group of this category? Okay, so pick modules over ENHF. I will just denote it by just pick of that spectrum. Okay, so so modules over ENHF is a symmetric monodal category where the unit is ENHF, and the product is smashing over it. Okay, great. Well, so let's see. So these spectra are periodic. What does that mean? That means that there is some suspension which, so there's a homotopy element in this degree which induces an equivalence. All right. So that means that if I take suspension, okay, so that's an element of PIG. That's invertible because suspension is invertible. And if I take all the suspensions, I will get a group. I'll get Z mod that MF, whatever it was. And that's a subgroup of PIG. Okay, so PIG will always contain a group generated by all suspensions of this spectrum, of this periodic spectrum. Okay, but now, so here's a question. Is there anything else in that group? Okay. Okay, and so I think today I'll be talking about the only known example where there is more than just that. So let me tell you some things that are known. So if n is 1, there is an interesting subgroup only at prime 2. And no, so pick E2, HC2, E1 is just generated by suspension. But actually I don't want to write all the orders. So it's you know what, how about this? I'm just gonna say no. Because I wanna get to the dirty stuff. So no. Then equals P minus 1. Also no. At n equals, so what else is known? N equals 2 be bigger than 2? No. And any n prime 2 group C2 also no. And of course, I have to attribute all these theorems. So this is Hopkins, Mahowald, Sadowski. N equals P minus 1. That's Hurd, Matthews, Stoyanovska. And please correct me if I'm missing some names. So n equals 2 prime 2. So that I think follows from a paper of Matthew and Stoyanovska. And the last one is Guccione, are you here? Help me. I don't remember. So it's
To Hurd and Denny.
Yes, okay.
To Hurd and Denny.
Hurd, she, and you, right?
Yes.
Yes, okay, great. Thanks. Okay, great. Okay, and then, so in all these cases, there's no other, there's nothing else in the Picard group. And now, so the one case where there is something other than just suspensions is this case. Okay, and so this is what I'll be talking about today. And this is joint work, in case I forget to state this later. So this is joint work with Agnes Baudry, Mike Hill, and Vesna Stoyanovska. Okay. Great. So now, before I talk about how to compute this, there is something else here that's kind of interesting. So I want to quickly, I don't know, talk about exactly how surprising this case is. So very quickly, the Morava stabilizer group at n equals 2 and prime 2 is given by the Witt ring, joint 1 generator. Sigma is the Frobenius, so one non-commutative generator up to these relations, and then units in that. And then there's a Galois group. I'm not going to be using it right now, but just for completeness. This is the Morava stabilizer group that we're looking at. Okay, at P equals 2. Okay, so what subgroups does it have? So it has subgroup C2, which is plus minus 1. It has, so you can see how there's an F4 in there, right? So, and there's units. So it has units of F4. It has C6, which is the product of the two groups I've just mentioned. And it has C4, which is kind of not very visible from the description. It has it actually has two groups of order 4. So there are two elements of order 4. I will not write them down because that will not be enlightening. Let's call them I and J. And then, of course, if you have two elements of order 4, you also have a group Q8. And there's a G24, which is this Q8 and this C3 acting on this Q8 by permuting I to J, J to K, and then K to I. So Q8 semi-direct product with C3. Okay, so this is a bunch of finite subgroups. And here I'm going to make a table. 2C6, C4, Q8, G24. Okay. And I'm going to write down how periodic these spectra are. And the PK group. All right. So here it's 16, and the group is Z mod 16. Here it's 48, and the group is Z mod 48. Here the period is 192, and the PK group is Z mod 192. And here it's 64. But so for C, here I'm going to change colors. For C4, the period is 32, and the group is Z mod 32 plus Z mod 2. Okay, so Z mod 32 is the part that you expect from the suspensions. The spectrum is 32 periodic, and then Z mod 2 is the surprising part. But what I wanted, like the reason why I made this table is I wanted to point out that somehow this very exotic stuff, the Z mod 2, disappears when we go to a larger group. So first, it was not present there when we considered smaller groups, then it appeared, and then it again disappears when we go to larger groups. So I don't know, I think this is interesting. But also, yeah, just this is the first known example of non-cyclic Picard group. Okay, so how do we compute this? Okay, so tools. So there are 3 different activities that we will have to do. And so tool number 1 is we use equivariant homotopy theory very much. Okay, so tool number 1 is a certain map, which I will describe in a moment. But before then, I have to talk about, so all I'm going to be talking about is only true for co-free spectra. So I have to tell you quickly what it is. So the Morava E-theory arises naturally as a G object. As a G object in spectra. Okay, not a genuine G spectrum. But I would like to use, as I said, I would like to use equivariant homotopy theory. So we have to fix this, and there is a homotopically meaningful way to fix that, which is given by something called co-free localization. Okay, so we consider a functor. Okay, so SPBG is G objects in SP. Okay, and SPG is genuine G spectra. All right, and so what we do is we take an R and we apply this function spectrum. Okay, and I'm going to be calling this RH in the future. Okay, and this is called the co-free localization or co-free displacement. Okay, so this functor takes equivariant maps, which are underlying Wick equivalences. To genuine equivariant equivalences. Okay, and it takes E infinity ring spectra. So this is what we actually we need. It takes E infinity ring spectra with E infinity G action to E infinity rings. in genuine G spectra, so I don't want to write this down. Infinite rings appropriate to this category. Okay, great. So this functor preserves all the properties we want. Okay, so that means that instead of studying modules over E over these guys over here, over E and HF, we can study F modules in the category of EM modules. Okay, so the homotypic category of G modules over R is the same as the homotypic category of modules over RHG. But this is the category of G modules. And this is free. This is true if R is co-free. Oh, R is co-free, and RHG to R is a faithful Galois extension. Okay, so the categories of modules are equivalent, so which means that the Picard groups are equivalent. All right, so this was all to get us to the point where we start studying this. For we will specialize later, but for now I'll just keep the notation R and G. So we'll specialize later to the case G equals C4 and R equals the co-free replacement of the second Moravec theory. Okay, great. Well, let's study that. There exists a map from the ring of G representations into this big GR, which is called which is that map that I advertised up here, JRG. And what does it do? Well, it takes a representation and makes corresponding sphere and smashes that with R. So now that's an excellent invertible GR module. Great. So that's one way to see some object in peak GR. Okay, so we can look at, we can try to understand the image of this map. Okay, so let's see what we can say here. So I have to give one definition. Let's say, so suppose V is a representation of dimension D. And our orientation for V is an equivariant map UV such that, okay, so what do we do now? So we take UV.
Irina, can I ask you a question?
Yeah. Hi, President.
Is the image of J surjective?
So it is surjective in all known cases, but we don't know how to prove it. So like in each case, you kind of just compute both, compute pic and compute image and see that they are the same.
Okay, I see.
But yeah, that would be cool to prove that.
Okay, cool. Thanks.
Yeah. Okay, so we take this UV and we smash it with R. Okay, so where do we go? We go here. And now we apply R is a ring spectrum, so we apply its multiplication map. Go here. Okay. And now this map has a chance of being an equivalence. And so if it is, then that the original map UV is an R orientation. Okay, and V is R orientable if it has an R orientation. Maybe I didn't need to write this down. Okay. All right, now here's a proposition. If it happens that if R is co-free, then being a representation V is R orientable is equivalent to it being in the kernel of the map J. Not it, sorry, of V minus D being in the kernel. Or in other words, V mapping to the same place as D does. Okay, great. So if we would like to compute the image of this JRG map, it would be great if we had a criterion for orientability. Okay, now this is where we get to the computational part of the talk. Right, so suppose we have an orientable representation. Suppose V is orientable, okay? That means that, I'm kind of rewriting what I wrote right up in the definition. That means that we have this map, which is G equivalence, okay? Great. Now let's we have a fixed point spectral sequence, right? So let's look at this part of the input to the homotopy fixed point spectral sequence. Okay, so this is H0, G, pi 0, R, and it has in particular an element 1 in here. Great. Now, this UVR gives me a map into here. And one maps to something here, which we will call UV. Right. Now that group on the right is also part of a homotopy fixed point spectral sequence. So I'm going to just write down both homotopy fixed point spectral sequences now. Right, so this is the one that's computing the ROG graded homotopy of RHG. And this one computes minus V plus D R. And UV R in this case gives me an isomorphism on the E2 pages. If I have this orientable, if V is R orientable, then I have an isomorphism. Okay. So, but it's an isomorphism on the E2 pages, right? Now, here's a theorem. V is R orientable if and only if UV is a permanent cycle. Okay, and it's sort of, so it's easy. It's easy to see it in this direction because if one is a permanent cycle and you have an isomorphism of spectral sequences, and one goes to UV, then UV is also a permanent cycle. It's a little bit harder to see it in the other direction, but also not very difficult. Okay, great. Oh, and maybe I should mention that, yeah, so I should write down that this is only true if R is call-free. And also V, this will be important in a minute, V has to be classically orientable. Okay, so we're trying to compute an image. So we're trying to compute an image of the map JRG. Okay, now we know how to identify its kernel. Okay, so its kernel consists of R orientable representations. And representations are orientable if the U associated to it is a permanent cycle. Well, so let's just go and compute a spectral sequence and compute the permanent cycle. Okay, so I have, okay, 20 minutes, okay. So maybe sort of change of gears for a little. I want to tell you about the spectral sequences that we have. So for a G module, M, I want to consider a Mackey functor. So this is the group cohomology Mackey functor. And it's, if you don't know what that is, it's something that encodes information about group cohomology, not only for G, but also for all its subgroups. Okay, so I don't have time to define what Mackey functors are, but so it's something that when you evaluate it on G mod K, you get regular, see there's no underline, regular group cohomology of K with coefficients in the restriction of M to K. Okay, so K is a subgroup of G. And it has standard group cohomology restrictions and transfers. Now, if we have a genuine G spectrum, there is the homotopy fixed point spectral sequence is a spectral sequence of Mackey functors. And I'm going to write it down. Okay, so it's also it's ROG graded spectral sequence of Mackey functors. Okay, so where we compute the Mackey functor group cohomology coefficients in the homotopy groups, and it converges to the Mackey functor like this, where I have to define, so I already defined what that is. Okay, so let me define what that is. So this is a Mackey functor such that if I evaluate it on G mod K, I just get the usual homotopy group of eCHT. Okay, so when I evaluate this spectral sequence, when evaluated at G mod K, it just gives me the standard, the usual homotopy fixed point spectral sequence for eCHT. Okay, so now remember what I was talking about. I have to, in the homotopy fixed point spectral sequence for RHG, if I can determine which UV are permanent cycles, then I will know which V are in the kernel of the map J. Great. So now we specialize. Remember, our group is C4 and our X is EH. And we compute the Mackey functor spectral sequence. for, I'm gonna sort of, I didn't say this, I guess you probably gathered that from what I'm writing. I will only talk about E2 right now, so E is E2. Okay. Okay, so we compute and we, right, so which representations are relevant? And I'm talking about the group C4. So there is the representation, which is rotation by 90 degrees. It's called lambda. It's two-dimensional representation. And there is sign representation. And there is two sign representation, right? So now sigma is not classically orientable. So it does not, we cannot apply this theorem. So it only applies for classically orientable representations. So we only want to look at those. And lambda and 2 sigma are classically orientable. Okay, so we are looking at corresponding u's. And we get that u lambda to the 8 is a permanent cycle. Actually, u2 sigma squared and u2 sigma times u lambda to the 4. All right. Now, a lot of differentials in this spectral sequence are computed by importing them from the Hill, Hopkins, and Ravenel computation of the spectrum K2. And so we are, so we're able to import a lot of differentials. So in particular, the fact that these two classes are permanent cycles follow from HHR computations directly. The last one does not, because that's a class for which the differentials for K2 and for eCHT4 are actually different. So this class supports a D5 differential in K2, so it's not a permanent cycle, but it becomes a permanent cycle in this spectral sequence because the target is gone. The target of that D5 is gone, and then you just show that it doesn't have D7, and then for dimension reasons, for sparseness reasons, it becomes a permanent cycle. Great, so right, so these are our permanent cycles. Now we are able to say something about this map. Okay. I'm going to denote this by ROC4 bar. And this is ROC4 modular the e-orientable representations. And also, so for reasons for which I don't have time, row 4 also has to be in the kernel of the J map. So J factors through RO bar C4. Okay, so let's compute what it is. So ROC4 is generated by 1 sigma and lambda. And then these permanent cycles here give me that 8 lambda minus 16 is 0. 4 sigma minus 4 is 0. And the last one you have to compute. So 2 sigma has dimension 2, lambda has dimension 4. So you get 10. So 2 sigma plus 4 lambda minus 10. And then row 4 is 1 plus sigma plus lambda. Okay, so you do some computation here, and you get this is Z-mod 32 generated by 1, and Z-mod 2 generated by 7 plus sigma. Okay, but that was just the first 2 out of 3. Because what did we do so far? We didn't actually compute anything. We computed that the J map factors through that. Now, it could happen that this 7 plus sigma ends up being when we do this map, right? When we go to pick, it might end up being some integer suspension as well. So it might go to the same Picard element as something from here. So that's step 2. Did I go 2? Maybe 2. We have to show that in pick, or rather, you can just smash. So it's eHC4 smash the sphere given by 7 plus sigma is not eHC4 smash with an integer sphere for any integer sphere. Okay. And in order to show that, that's really just a computation. We literally compute. So we compute the ROG graded spectral sequence, right? Which means we know the homotopic groups of this, and we know the homotopic groups of this for all M, and we just compare them, and we see that there is no way they'll be ever the same. I can actually maybe show a picture right now. So, no, not this one. I'll show in a minute. Okay. Great. Okay. So this is the integrated computation for E2HC4. It's in terms of Mackey functors, so it encodes simultaneously C4, C2, and the trivial group information. And so there are differentials, but to make my point, I just want to show you the answer, right? So there's some answer that we obtain. And that's just the projection to the integer grading. Okay. Which means that, yeah, so we compute this part for all M. Great, now let's go and compute. So this is the sigma. This is the, how do I say this? It's a projection to the homotopic groups indexed by these spheres, okay? So we computed, and we get an answer. And that answer is very different from the integer graded homotopy. And at no shift does it coincide with the integer graded homotopy. So, okay, so you just compute that. And that means that we have, so using tool 1 and tool 2, we know that the minimum our Picard group can be is Z-mod 32 plus Z-mod 2. Okay, so we know that that's in pick. All right. But it can also be larger than that. So now we have to compute the upper bound. And here we use the Picard spectral sequence. It's yet another tool, Picard spectral sequence. Okay, so maybe just very briefly for those of you who don't know what that is. So if I have a Galois extension, then there is, I'm really abbreviating a lot of stuff here. There is a spectral sequence which given, so this is something called Picard spectrum. So G acts on R, G also acts on the Picard spectrum, and there is a spectral sequence which computes, so this is a homotopy fixed point spectral sequence, it computes Pic R HG, which happens to agree with Pic R HG. Okay, and so here when I write small Pic, that's the Picard spectrum, and then the Picard group well, actually, the Picard group of anything is pi 0 of the Picard spectrum. In particular, Pic RHD is pi 0 of Pic, and now you can choose. You can choose how to think of it. Okay, right. So for a genuine G spectrum, the Picard groups for different subgroups assemble into a Mackey functor. So for genuine G let's say Pic G R is Pic RAG, and for subgroups H in G, Pic H assembles into a Mackey functor. Which means that we have a Mackey functor spectral sequence. We have a Picard spectral sequence of Mackey functors. Oh, maybe I should call this. This is the Picard spectral sequence. No, I already said this upstairs. Okay. Okay, so we compute it. Okay, so let me tell you. Let me write it down. In our case, it's Mackey functor cohomology. And we just need to compute its pi 0. I'm defining the right side. Okay, so pi 0 of it is a Mackey functor evaluated on H. It gives you Pic H, like I just promised here. It gives you the Picard group like this, which is the same as the Picard group of EHH. And this is the same as this. All right, so now if you want to know more about this, there's a paper. So this has been, the way we use it has been developed in the paper by Matthew and Stoyanovska. And in particular, they prove that the Picard spectral sequence agrees with the fixed point spectral sequence in a range. And then that turns out to be the range that computes most of it, most of what we want. And then they give other tools to do more computations. And what we get in the end is, I will show a picture in a minute, that we get that order of Pic EHC4 is 64. Okay, so the largest it can be is 64. Actually, sorry, we don't get that. We get that the order is less than 64, less than or equal to 64. But we already know that we have to have at least 64 from this. Okay, so that's it. So that concludes that pick is actually that. Okay. And I'm done. I just want to show you a picture. So this is the Picard spectral sequence. The left side is D3 differentials in it. The right side is all the higher differentials. It's in Mackey functors, so there are like all these symbols. So it encodes simultaneously the Picard spectral sequences for E itself, eHC2 and eHC4. And the black differentials are the ones that are easy, and then the red ones are the ones that are hard, but there's a formula. Matthew and Stianos give you a formula. And we really, this is the last sentence I'm going to say, we really use the fact that we have a spectral sequence of Mackey functors because Matthew and Stianos give us, so there's a theory that allows us to compute these differentials. Okay, so D7 and D5 and D7. But there's no theory that allows us to compute this D11, except if we use the fact that there is this exotic extension and there is a similarly exotic extension in this Mackey functor, which means that this D11 has to follow from this D7. If we were not considering a Mackey functor Picard spectral sequence, we would not have been able to compute that differential, this D11. Okay, I'll stop here. Sorry for going over time.